All right, welcome everybody. Thank you for your understanding with my issues yesterday. My son fell off the monkey bars at school and broke his collarbone. So that was a day. But here's the video from yesterday, and I'm also going to put the video for tomorrow's lecture, which was 8.1. So today we're talking about 7.4. Tomorrow's lecture, if you want to watch it all in one go, is going to be tacked on here for 8.1. If you want to just pause it and watch it tomorrow, you can do that. But they'll just both be here. One other note is that if you're looking up here, the whiteboard program that I use is now changed. It looks different and it has different functions, and some of them are not good. They took away some of the features I use, so the flow of my whiteboard over here may be just a little bit different because I can't do certain things anymore, and not quite used to this version of that whiteboard, but it is what it is, and here we go. 7.4 is nonlinear systems of equations. That everything that we've done up to this point has been linear, and now we're going to talk about what happens when it's not linear, right? So one of the things that we'll look at is something like this. So once I get squares or things that are not just x's or y's or whatnot, now it's not linear. It's not going to be a straight line. But if I have this, I've got x squared plus y squared equals 25. And we're talking about systems, so I would have two equations or more. And that would then be, let's throw this one in there. Right? And you might recognize this one to be a circle. It's got a radius of 5, the square root of that 25. And it's centered at 0, 0. Right? And then you might recognize this one as a line. So I have one linear equation here, but the system itself is nonlinear because one of my equations is not linear. But it would make sense then, right, to think about what's happening. I've got a circle, right? Get this out of here. There's weird stuff you can do here. If I click this, hey, look at that, it's a circle, right? But if I have this circle and I have a line, I have options as to what's happening, right? The line could totally miss. If it totally misses, there's no solution, right? Or the line could come and touch, and there are a few things that are nice here. I can draw a straight line just by hitting shift, but I might have the line come and just touch the edge of the circle, right? This line is then called a tangent line because it only touches a circle in one spot. And if that's the case, then I have one solution, right? This, wherever it touches, right? But my other option is that this line might go through the circle and touch it at 2 points, right? So it is valuable to be able to visualize what's happening with the shapes and things like that. Sometimes you can't because these equations can get a little bit hairy, but those are my three options. I'll either have no solution or one solution or two solutions, right? But how do I go about solving this? Well, what I would do is solve the bottom equation either for the x or the y. It doesn't really matter which one, but I'm going to isolate one of those. Because this x is already positive over here, I'm just going to add 4y to both sides of this equation and isolate the x. If I divide each side by 3, then I have x equals 4/3 y. Right? And I can take that 4/3 y and replace it into the x of the other equation, right? So if I do that, that becomes x, which is now 4/3 y squared plus y squared equals 25. Can't see anymore. Let me scoop this thing over. There we go. And then just solve this, because now it's a system. It's still nonlinear, but it's a system of only one equation. That is something I can deal with, right? So if I square 4/3 y, that gives me 16/9 y squared plus another y squared is equal to 25. But if I'm adding these, they're like terms, they're y squared terms. I can call this, let me just give myself a little more room right there. I can call this 9/9 y squared, because that's still 1y squared. And then I get 16y squared plus 9y squared all over 9. That's 25/9 y squared equals 25, right? To isolate the y completely, I'm going to multiply both sides by 9/25. That cancels out 25s. It cancels out the 9. That leaves me with y squared is equal to 9. And then if I continue, I can square root both of these, and that gives me that y is either equal to the positive or the negative of the square root of 9. So y is positive or negative 3, right? So there's going to be two solutions because I get that plus or minus. And all I have to do is take this back up and plug in those solutions in and solve it for x. And I'm going to plug it into the easier of the two equations. That is, I'm going to plug it into this. Right? So I'm just going to rewrite that down here. 3x minus 4y equals 0. That's not helpful. 3x minus 4y equals 0. So if I plug in y is equal to a positive 3, that gives me 3x minus 4 times 3 is equal to 0. Or 3x minus 12 is equal to 0. And if I add 12 to both sides, that gives me 3x equals 12. And if I divide each side by 3, we can see that that gives me x equals 4. So that was x equals 4 when y equals 3. That gives me the point 4, 3 as one of my solutions. Okay. And if I plug in the other one, if I plug in y equals negative 3, then I get, that's not helpful either. If y equals negative 3, then I get 3x minus 4 times negative 3 is equal to 0. But that is 3x plus 12 equals 0. And minus 12 to both sides. 3x equals negative 12. We can see that we're just going to get the opposite value here. Divide each side by 3. X equals negative 4. So that is to say x is negative 4 when y was negative 3. So that gives me the point negative 4, negative 3. And I do indeed have the situation where I have two solutions. All right. Let's take a look at another one. I'm going to just erase one of the things is that I can't just erase my entire screen, which drives me crazy. But if I don't erase it, the whiteboard's going to start lagging. So bear with me while I clean up this garbage. I don't know why they call it an upgrade when they lose features. That drives me crazy. All right, there we go. I apparently can't get rid of that for some reason. There we go. Boink, get out of here. Get out of here. What is this crap? All right. There we go. Let's take a look at the next one. Let's do this guy. X plus y equals 5. And y equals 3 minus x squared. All right, so visualizing what we have, this first one is a line. It's a linear equation. But the other one is a parabola because I have this y equals x squared. And so, again, I have three options, right? It's a upside down parabola because it's a negative x squared. So that'll look something like that. Wherever that ends up being, it doesn't matter. My three options are I could miss the parabola with my line completely and have no solutions. Or I could come and, again, wow, that's not a great line. Come and touch it at one point, and I have one solution. Or I could go through the parabola and hit it twice, right? So I have those three options. All three of them are possibilities. So I have no solutions, one solution, or I have two solutions. It's not possible to get any others because a straight line only has those three options. You can't come over here and say, well, what if the line is like this and it touches it in infinitely many places? It doesn't, because the parabola is going to move over and there's only going to be one spot there, right? If you zoom in, you'll see that no matter how steep the parabola is at that point, it's still only going to just touch in one place. So I would maybe solve for this y right here by subtracting x to both sides. That leaves you with y equals either 5 minus x or negative x plus 5. It doesn't really matter how you look at this, right? That. But I'm going to take this 5 minus x and plug it into the y over here. So that gives me 5 minus x equals 3 minus x squared. Once again, I've eliminated the y. It's all in terms of x now. And so I need to just solve this. So I'm going to drag everything to the left-hand side by subtracting 3 and adding x squared. So minus 3, add x squared. Oops. And that gets me, here I'll write this as x squared. And I'm going to write my minus x first, just to put this in descending order. And then 5 minus 3 is plus 2. And then on the right-hand side, I have equals 0. I should be able to factor this, right? This would end up being x minus 2 times x plus 1 equals 0. And then use the factor theorem, the zero factor theorem, that says if two things multiplied together equals 0, then either one of those things is 0 or the other of those things is 0, giving me two equations that I just solve. Plus 2, minus 1, minus 1. So x is either equal to 2 or x equals negative 1. So it appears that we're going to end up with two values, right? Oh, we got to back up. I got ahead of myself. This is wrong. Because that is not the factored version of this. Because if I FOIL this back out, I get x squared minus x, but I get minus 2, right? So this is not the same. This I messed up on, so everything I did after it is garbage. I apologize. But can I factor this? And the answer is no. It doesn't. It's a prime factor, right? And so that's a pretty good indication that we might not have a solution here, because I got down to a trinomial that I factored incorrectly. But if I want to go and factor it correctly, I can't. It's not factorable, right? So let's take a look graphically at what we're dealing with. The parabola was y equals 3 minus x squared. I would write this, if I'm graphing it, as negative x squared plus 3, right? It's an upside down parabola, meaning it's facing that way. That's been shifted up by 3, right? So 1, 2, 3, and it just looks like this, right? But if I graph the line, that line was x plus y equals 5. I would subtract the x to the other side to get y equals negative x plus 5. So that's just a line with slope -1 with an intercept of 5. Right? So that is up here. And if it's got a slope of -1, it's going to look like that. And these guys don't touch. So there is no solution. Right? Because if I do try to factor, I mean, just because I can't factor, I can still use this. I can plug that into the quadratic formula, right? And even though I botched it down here, let's just get rid of that. Let's just pretend that didn't happen, right? I don't make mistakes. This equals 0. So if I use the quadratic formula, that is x equals negative b. B is -1, so negative b is +1, plus or minus the square root of b squared. So -1 squared is 1, minus 4 times a times c, all over 2a. But I get 1 plus or minus the square root of 1 minus 8, all over 2. And it's having this negative under that square root that tells you this is not going to work out. Because this is a 1 plus or minus root 7i all over 2, right? So there's not going to be any real solutions here, and therefore that's why these guys on the real plane, they don't touch. Okay. Some of the more difficult ones, we talk about the next guy that we're going to talk about. Let me clear this out. My whiteboard's getting a little bit slow. I think I can just clear the whole thing out by just deleting that. Maybe. There we go. Let's look at this guy. I have 2x squared plus 5y squared equals 39, and 15x squared minus 5y squared equals -5, right? Now this first one is an ellipse, right? And this is why now it's ellipse. This is why it's hard to visualize this, because we haven't talked about ellipses and we haven't talked about some of these other shapes. But an ellipse is essentially like a football shape, of an oval shape, right? But the other one is a hyperbola. And that is essentially two, not quite parabolas, but two things that kind of, like if you took that oval, split it in half, turn it around and let it run off to infinity, kind of an idea, a little bit. Not exactly, but sort of. But again, we're not going to get terribly in depth with those. And in fact, we skipped almost all of the conic, not almost, we skipped all of the conic section that talks about how these things are and what they look like. And you would go more in depth in the future class for those. But since we can't really visualize that, what I can do is use what we've, done in the past. I've got a plus 5y squared and a minus 5y squared here. I can use that elimination method simply by adding the two equations together. So if I have 2x squared, 15x squared, that gives me 17x squared. The y's are canceled. So this equals 34. Well, how convenient, because 34 is divisible by 17. Leaving me with x squared equals, well, 2. That's a little less convenient, because if I take the square root, then I get x is the positive or the negative of the square root of 2, right? So it looks like I'm going to have two answers here, right? So if I plug in, let's go with the positive root of 2. Plug it into one of them. Doesn't matter which one. I'm going to do this one just because it has a smaller number in front of the x squared. But if x is the square root of 2, that gives me 2 multiplied by that square root of 2 squared plus 5y squared equals 39, right? I'm going to pause here because there's a symmetry that's going to make life a lot easier if we can recognize it. I'm also over here plug in x equals negative square root of 2. And if I do that, I get 2 times the negative square root of 2 squared plus that 5y equals 39. Right? But both of these are the same thing. If I take the square root of 2 and square it, I'm just going to get a 2. But if I take the negative square root of 2 and I square that, I'm still getting a 2, right? So it doesn't matter which one I'm doing, the answer is going to apply to both of them. So I'm going to say that this applies to both positive or negative root 2, just to save me the work. Okay. And then I get 2 multiplied by, this is just 2, plus 5y squared is equal to 39, or 4 plus 5y squared is 39. If I subtract 4 from both sides, then I've got 5y squared is equal to 35. And if I divide each side by 5, then I end up with y squared equals 7. And again, if I take the square root here, then I get y equals positive or negative root 7, right? But again, this applied for x is both the positive and the negative square root of 2, so there's actually 4 answers here. If x is the square root of 2, I get both the positive or negative root 7, so I get root 7. But I also get, if x was root 2, I get negative root 7. But this also applies to if x is negative, so I should have negative root 2 and root 7. And also negative root 2 and negative root 7. And so there's 4 answers, which makes sense with these shapes. And again, I know we skipped all of this, but the first shape was an ellipse. The second was a hyperbola. And so we do indeed smack or cross 4 times total. And that's where that happens. Okay. All right, let's take a look at this next one here. The idea, the overall idea here, though, is if you can't visualize it, and for a lot of these you won't be able to because they're just, you know, a little bit crazy sometimes, is to be able to eliminate one of the variables, however that happens, and then, so all right, this takes forever. Freaking hate this. Let me just yoink, yoink. There we go. Okay. Oh, look at that. Let's look at this guy. So I have x squared minus 3y squared equals 6. And I won't even mention what these shapes are, right? Okay, I will. I lied. This is a hyperbola, but that doesn't matter. Let's pretend we don't know that. The other one, this xy equals 3. I don't know what shape that is. I do. I'm just not going to tell you because it doesn't matter. What I want to do is figure out how to get rid of one of these variables. And I can't use the addition method that we just used because I don't have an x squared to eliminate in my second equation, and I don't have a y squared to eliminate in my second equation. But what I can do is the substitution method, right? If I take this second equation and let's just say divide by x, that gives me y equals 3 over x. And I can take that and replace the y in my other equation. I'll do that down here. That leaves me with x squared minus 3 times y, which is 3 over x. That's squared, and that all equals 6. Now I have just an equation with x's, right? So I'll clean it up. This gives me x squared minus 3 times, if I square that, that's 9 over x squared equals 6, right? And if I clean it up just a little bit more here, oops, move these. This ends up being x squared minus 27 over x squared equals 6, right? This is not the easiest thing to deal with, but I can still deal with it, right? I'm going to multiply everything by x squared. Multiply the left by x squared. Multiply the right by x squared. And if I do that, I'll distribute the x squared through here. That gives me x to the 4th. But the x squared just cancels the x squared here, so I get just minus 27 equals 6x squared. Now I have no more x's in the denominators. That's nice, because now I can factor this guy down. I'll start by subtracting 6x squared to both sides. So I have x to the 4th minus 6x squared minus 27 equals 0. Right? And I can factor this because x to the 4th, right? If you use, like, say, a lot of people like to call it a u substitution. And I'm going to say, let's just let u be equal to x squared, right? Because I have this x to the 4th, which is x squared squared, and x squared. And if u is x squared, then u squared is x squared squared, or x to the 4th. And I just replace this. X to the 4th is now u squared. 6x squared becomes 6u minus 27. And this guy is easy to see that it factors down to u minus 9 times u plus 3. Right? Now that I've got the factor down, I'm going to replace my u with my x squareds. So this is x squared minus 9. And this is x squared plus 3. And I can factor x squared minus 9 further, because that's the difference of two squares. So this becomes x plus 3 times x minus 3 times x squared plus 3 equals 0. And I use the zero factor property that says if I have a bunch of stuff multiplied that gives me 0, then the first is 0, or the second is 0, or that third one is 0. So I have 3 equations. Right. I can solve this guy, just -3. That gives me x equals -3. Solve this one, add 3. That gives me x is equal to 3. But I can't solve this one, because if I try, I get x squared equals -3. This is not going to be real. So I dismiss it as a possible solution, because that's what I'm interested in. I'm looking at the real intersection of these values, right? Unless, of course, we're not. All right, let's back up, actually. So not real, but at this point, let's just say, what if we don't care, right? Then I get x equals plus or minus square root of -3, or x equals plus or minus I times √3, right? So I'm going to have 2 real solutions. And 2 imaginary, or 2, let's call it complex, right? So what I'm going to do is take those values and plug them into this original equation right here. Was x times y equals 3. I'm just going to plug in my x values into here. Those x values were, first one, let's say, is x is equal to -3. That gives me -3 times y equals 3. And if I divide each side by -3, I get y equals -1. Giving me the point, x was -3, y is -1. That is one of my solutions. The next x value was x is equal to +3. And if I plug that in, then I get 3 times y equals 3. Divide each side by 3, I get y equals 1. So that is to say, when x was 3, y was 1. That's my second solution, right? Now I have 2 more. X could be equal to I times the square root of 3, right? From this guy. That's the positive one. And if I plug that in, then I √3 times y equals 3. And so I would divide each side by I √3 if you want. I √3. The √3 is going to cancel out. The I is going to cancel out, isolating my y. And so I have this kind of horrific looking garbage here. I √3 in the denominator. You can and probably should rationalize this. And I would rationalize this by multiplying both top and bottom by that I √3. Because if I do this, then this becomes 3 I √3. It's just those 3 things multiplied. And the denominator, an I times an I, is a -1. And then a √3 times a √3 is just 3. The 3's can just cancel out. The negative can come out front. And so this ends up being negative I √3, which is to say that when x was I √3, y was negative I √3. And that is my third solution, my first complex solution. And then for my last guy, I'm going to say what happens when x is equal to negative I √3. But then I have negative I √3 times y is equal to 3. You can see with the symmetry here that we're going to end up with y is equal to a positive I root 3. So that is to say, when x was negative I root 3, y was positive I root 3, and that's my final solution. Is all 4 of those values. So kind of a big one, kind of hairy, but if you are supposed to find all solutions, including all of the imaginary or complex ones, that is how you would do it. Okay. Let's look at the very last thing they talk about in here. Let me clear this out and get a new one. Not, oh, couldn't be deleted. Cool. That's a great feature. And I can't create a new one. What is happening? None of this is helpful. Cool. All right, let's get back in here. Okie dokie. Cool. Well, awesome. This is just fantastic. Thanks for upgrading my awesome whiteboard, Microsoft. Well, that drives me crazy. This is dumb. All right, let me stop sharing this for a second and try the whiteboard here. Google's got one. Let me try it. I remember not loving it. But I need something that's going to work here. So that. Okay. All right. Well, there it is. See, I don't know how to use this, but here we go. Seems just the same. All right. All right. Let's do this one. The last thing they talk about is what if we have a system of inequalities, right? So what if I have y is less than or equal to, there's a delay on this one that drives me crazy, but here we go. Y is less than or equal to 4 minus x squared, and x plus y is greater than or equal to 2, right? So the first thing that I want to do is graph the boundaries. Those boundaries are going to be if there's an equal there. So the boundaries are at y equals 4 minus x squared. And this one's going to be solid because of the inclusive inequality that we started with. And the other one is just going to be x plus y equals 2, which is also solid because of the inequality that we started with, right? So I should know what both of these look like. The oh, that's all the screen I get. That's cool. Not really. But I should know what these look like. I should be able to say this first one is a parabola that starts here at 4, is the vertex, and it's an upside down parabola because it's a negative in front of my x squared. And so it looks like that. Okay. This other one, if I minus x, it's easy to see that I have y equals negative x plus 2, straight line with a slope of -1 and a intercept of 2. And so I have a line that does something to this effect, right? Now, I would want to test, and I'm going to have to erase some stuff because this is all the board I have on this program. I want to test some points. So let me erase this stuff over here. I miss my old whiteboard. I don't know why I can't just have the old one that worked back. But here we go. I'm going to test a point. 0, 0 is a good point. It's just sitting here, right? So I'm going to test 0, 0 into the first inequality, right? So that would be 0 is less than or equal to 4 minus 0, or 0 is less than or equal to 4, which is true. And so since I tested it in relation to this parabola right here, that means that I would shade where 0, 0 is, which is underneath that parabola. I'm on a whiteboard, so I'm going to try not to make it look horrific, but that's everything under the parabola there. So I have two options. I could either have a solution in this region up here, trapped between the line and the parabola above the line, or I could have a solution down here. I don't know if you can see that green, but that would be the area trapped below the line, but still within that parabola, right? So I'm going to test 0, 0 again into the line to see if I'm above or below the line. But into that equation, or that inequality, I have 0 plus 0 is greater than 2, or 0 is greater than or equal to 2, but that's false. And so it's not down here where 0, 0 was, it's the other area. And so my solution is indeed the upper part up here. And that is the solution space, right? So it's the same as graphing inequalities in the past. Now we just have nonlinear inequalities. So you simply have to take into account that they're not always going to be straight lines. All right. Hopefully that helps with that section. That's it for 7.4. I'm actually going to stop this video now because there's no way in hell I'm doing the next section on this whiteboard. So I'm going to cut this into 2 videos. So look for 8.1 as soon as I can get my other whiteboard to pull its head out of its keister. Thanks, and I'll see you next time.